Now let's look at some examples that use the multiplication rule. In this example, you're taking a 2-question quiz. The first question is true-false. The second question is a multiple choice with 5 choices. So say you didn't study for this quiz, you are completely guessing, you have no idea, so you're randomly guessing. What is the probability you answer question 1 and question 2 correctly? And tells us this is the multiplication rule. It doesn't say or, it says and, that key word. Okay, so we want the probability that we're correct and correct. Those are the results for question 1 and question 2. Well, one way we can consider this is visually in what we call a tree diagram. Let me write that down. A tree diagram. And that visually shows us all of our outcomes, all of our possible choices. So, in the first branches of our tree, this represents our first question, and we could answer either true or false. So we either go down the true branch or we go down the false branch. Now we're done with that. We're on question number 2, and question number 2 we'll either answer A, B, C, D, or E. And likewise, if we went down branch false, we would have those same 5 choices: A, B, C, D, or E. So the tree diagram ends up showing us how many different outcomes we have. We can just count these termination points. One outcome would be true A. So let's show what the sample space would look like here. So one choice we could make would be true A, or we could pick true B, or true C, or true D, or true E. Or if we went down the false branch, false A, false B, false C, false D, or false E. And that's it. That's our entire sample space. So we can either count the number of termination points we have here in our branches, or count here, and we'll see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes. Okay, so how many of these will get us correct and correct? We'll have that result. Well, obviously only one. Only one of these is the result of the correct answer for question number 1 and the correct answer for question number 2. If you're randomly guessing, then this is a problem where you have equally likely outcomes, right? So the probability that you guess correct and correct, well, there's only one way to do that out of 10 possible outcomes. Another way to calculate this, other than counting, writing all this out, is what the multiplication rule shows us. So we'll come back here now and look at our branches and assign a probability to each branch. So if you're randomly guessing, what's the probability that the answer is true? Well, it'd be 1/2. That the answer is false, 1/2. There's one way to get true out of 2 possible choices. Okay, so on the next branch, our second question, then the question is, what's the probability that A is true? Well, A is 1 question out of 5. So I didn't leave enough room here, but each one of these little branches would be the same probability, correct? 1 out of 5 all the way down. See if I can fit those in. And of course that wouldn't change here. If we come down this branch, then the probability of A, that's 1 out of 5 choices, and B is 1 out of 5, and 1 out of 5, and D 1 out of 5, and E 1 out of 5. Okay, so Another way to look at this, the probability of correct and correct on the first one. Let me put a little subscript. How about that? Correct on 1, correct on 2. That might help us understand this a little better. Okay, is the probability that we're correct on 1, question 1, times the probability we're correct on question 2. So 1 was 1/2, 2 is 1/5, so that's where another way we can see that computation of 1/10. Okay, let's look at another example. This time we have an urn that contains 3 red balls, 4 blue balls. We've got 3 and 4 blue and 5 white balls. If you randomly select 2 balls, one at a time, find the probability that the first ball is red and the second ball is white. Okay, so we could write that in sort of a shorthand. Probability of red and white. Now it doesn't say or, and. So we know this is telling us we're going to use the multiplication rule. Well, let's look again at our tree diagram, see if we can construct one. So on the first draw, we could get a red ball, we could get a blue ball, or we could get a white ball. Okay, on the second draw, we again could get another red ball, or blue, or white. Likewise, if we went down if we'd selected a blue one the first time, we still would have the option of getting a red, a blue, or a white. And finally, if we drew a white ball first, we still, could get a red, a blue, or a white. Okay, let's assign probabilities to these branches. So, the probability you reach in and you get a red ball. What's the probability? Well, we need to know how many balls are in the urn, don't we, to understand what our probability is on that first selection. So we had the number in the sample space then is 3 plus 4 plus 5 or 12. So there are 12 balls in the urn, and the probability that we select a red, well, there are 3 red balls. So we have a chance of 3 out of 12 getting a red ball on that first draw, that first selection. There are 4 blue balls, so that we have a chance of 4 out of 12 of getting a blue ball, and there are 5 white balls. So we have a chance of 5 out of 12 getting a white ball. But now, before we make our next selection, do we have a question? Is there something we need to know about this situation before we can answer the next part of the question? We need to know how this procedure is being conducted. So we need to understand what happens to that first ball after you select it. Did it go back in the urn, or is it left out on the table? Okay, so our results here are going to be different depending on what's done with that first ball. So let's assume the first ball is replaced. So we'll work this problem first by saying replace first ball. Okay, so if we know we replaced the first ball, then we essentially have the same urn sitting there on our second draw. We put all the balls back. We pulled one out. It might have been red, it might have been blue, it might have been white. We notated what it was, and then we put it back. So what's the probability of now, if we drew a red one first, that we draw another red one? Well, there's still 3 red balls in the urn, and there's still 12 balls in the urn. total. There's still 4 blues out of 12. There's still 5 whites out of 12. So all these branches would still say the same thing. I can't fit it in there, I'll just put it here. Okay. 12, 4 out of 12, 5 out of 12. So with replacement doesn't change the probabilities at all. We're back essentially to the same situation on our second draw. So the probability of red and white, as we saw before, we could multiply. So the first ball is red. There was a 3 out of 12 chance that that would happen. The second ball was white, and there was a, if we went down the red branch, now white, 5 out of 12. So multiplying numerator times numerator, denominator times denominator, we get 15 over 44. We can reduce that to 5 over 48, or write it as a decimal to 4 decimal places, 0.1042. Okay, so we said that's the condition of A, where we replace the first ball. But let's consider now without replacement. Of the first ball. How is that going to change anything? Probability of red and white. Well, it doesn't change the first draw. That's still, we have 12 balls in the urn. We select a red. That probability is 3 out of 12. But now there's a new condition. We have set aside that red ball. What's the probability on the second draw that we draw a white ball? Well, there's still, because we've only removed a red, there's still 5 white balls in there, so we know this numerator's 5. However, there are no longer 12 balls in there. We have set aside the red ball. There are only 11 left in the urn. So now our probability turns out to be 15 over 132, which will simplify to 5 over 44, or to 4 decimal places, 0.1136. So we can see we got a different result, and it was important to know what the procedure entailed. Is it with replacement or without replacement? So we have to know that. Without replacement puts a condition, a new condition, on the procedure and makes a difference in how we calculate. So we will look further in when we talk about, I'm talking about this word condition, on conditional probability in another video. Here we just wanted to notice that there is, with regard to the multiplication rule, we do have to know whether and what the procedure entails, whether there's a condition or there is not a condition. This is, keep in mind, this is kind of similar to the fact that with the addition rule, it was important to know whether the events were disjoint or not, whether or not they were mutually exclusive. That gave us a different way to calculate the addition rule and calculate that probability. So likewise with the multiplication rule, we need enough information to know if this is with replacement or without replacement. And without replacement, that means there's a particular condition now that we need to consider. So we will look at conditional probability in another video.